You go, Susan.
Welcome, everybody. I'm Susan Couch and a member of the Science, Medical, and Technology Committee. And as we enjoy this beautiful warm day and our air conditioning, most likely, we're going to learn a little bit about the electric grid today. My husband and HASS member, David Couch, is going to be the presenter. He's a retiree from Spartan Nash, where he held the position of Senior Vice President and Chief Financial Officer. And he did that for 22 years with a 30-plus year career with Spartan Nash. He had the responsibility of all the business systems, technical infrastructure, communication technology. In addition to his work at Spartan Nash, he has worked at several other large corporations, accumulating over 50 years of experience in the industry. He holds a bachelor's of arts degree in business administration and a master's degree in computer science from the University of Arizona. So I'm going to kick it over to David.
Okay. So one thing I do want to correct is that I was not a CFO. I was a CIO. I'm not a financial genius, but I've been in the computer business for a long time. So and just in regards to that, while I spent my career in computers and communications technology, you might wonder why I'm talking about the grid. Well, I've had a lifelong interest in electricity. I blew my first fuse when I was 6 years old, and I think it was a fuse in those days. But anyhow, I've always had a fascination with utilities and electricity and so forth. And so after having read several books and studying lots of things, I did meet with Dave Koester of BPW to have him check my work to make sure I wasn't I was communicating properly and had the right information. So anyhow, and he helped fill in some of a few details that I didn't have. So with that, I'm going to share my screen, and let's see. Can everybody see my slides?
Yes.
Yes.
Great, thank you. Okay.
Except David, right now you're currently, oh, there we go. Never mind.
Okay.
I thought I could see your desktop, but you're great now.
Okay. So, and one thing to let everybody know, I'm going to take most of the time of the class. I've got a lot of material here. Talking about the electric grid is not necessarily a trivial thing. And so, but I'm also, you don't have to have a degree in electrical engineering. I certainly don't. And I'm only going to talk about some basics of electricity to give you some foundation as we go through it. So my plan today is I'm going to talk about some basic principles of electrical systems, not in depth, just to kind of give you some facts to work with. We're going to talk in detail about the Holland BPW grid, because we are very blessed in Holland to have a modern, well-run electric utility that's a good tool to sort of explain how electric utilities work. Then we'll expand out and talk about the grid within the state of Michigan, talk a little bit about that environment. And then we'll focus on the national grid. We'll talk about the history of it, how it got started, how it's evolved into what it is today. And we'll talk about what it takes to manage the grid and the things that go on behind the scenes that give us the energy that we all depend on so much. And then we'll talk about what happened in Texas. And I have to be careful here because I could make lots of snide remarks, but I'll try and remain professional as I go through the details in Texas. And then we'll have a little summary at the end. So let's talk about some basic principles of electrical systems. We'll talk about generation sources. We'll talk about the transmission system. In fact, right up front, when we talk about this, when we think of the grid, we think of it in three groups. We think about the generation of electricity, the transmission of electricity over large distances, and then the distribution system that gets the electricity to your home. And we'll talk a little bit about what goes on in your house as well. So one of the first things to understand, and I'm not going to get into gory details here, but there's two basic kinds of voltages or current, and not voltage, two types of current that exist. And one that you all know, that if you have a laptop or if you have a flashlight or you have a cell phone, those devices all run on something called DC current, which is a current that runs at a constant voltage, and it is wonderful for small devices, but if you want to move large amounts of electricity over large distances, DC is very, very difficult to deal with. It doesn't have the flexibility that AC does. So the grid that we live and thrive on in this country runs on AC current. It is an oscillating current that changes directions 60 times a second. And so it goes from 0 to a positive voltage and back down to negative and back to 0 every 60 times a second. That alternating current, we're not going to get into any more details than that, but the thing that's important to know is that it is much more flexible in things in terms of being able to change voltages and transmit the electricity over large distances. It is a much more flexible type of current to work with than DC. And so that's why our electric grid is built around AC as a type of current. So then the other thing, and I only say this because if you look up in the air and you see wires on poles, you typically see them in threes. And the reason that you see them in threes, I have a little animation in the upper right of what a generator looks like. And so a generator, you see a magnet rotating, and you see a pair of blue poles, you see a pair of red poles, and you see a pair of green poles. And what those are is a way for us to generate more electricity per revolution of a generator. And so it's much more efficient to generate. And it creates that three phase. You can see the little graphic in the upper right. If it creates the three phases of voltage, and it creates that 60 hertz oscillation, and each of the poles is, if you will, a third offset from the other. So if you look down at the bottom on the lower left, you'll see in a 60-second cycle, the blue, the first phase. Then you'll see a red cycle, and this is they identify as a third phase, and the yellow is the second phase. The point is that there's 60 cycles in each one of these phases, but it's more efficient to generate because we got 2 or 3 sets of energy coming out of that generator for one revolution. It's easier to transport. The wires don't have to be as big. And so it's just how our electrical system is built in this country, the 3 phases. So that's why you always see 3 wires. The next thing that's very essential to all this is transformers. And so when generators generate electricity, they generate electricity generally in the 10 to 15,000 volt range. But to move them over miles and miles, tens of miles, hundreds of miles, it's much more efficient to take that electricity and generate it up to, or transform it up to a higher voltage, 138,000 up to 250,000 volts, 1,000 volts. And so there's a transformer that does that. You see that below the graphic. And then once it gets to its destination where you want to work with it, then you step it down to a lower voltage. And so the voltage on the poles around which we drive is typically in Holland, it's either 12,000 or it's 7,000 volts. And then when it comes to your home, it goes through a final step down transformer, and it could be in the ground, depending on the neighborhood and how the utility is delivered to your home. If it's on a pole, there's a transformer that steps it down to 240/110 volts. Or if it's in the ground, you'll see a transformer like that in your neighborhood. And there might be anywhere from 3 to 5 homes on each transformer, depends on the size of the home and the amount of energy they draw. So transformers are a very critical component it allows us to move change the electricity so we can move them over great distances. And that is something that is very unique to AC voltage. So that's why we have that AC, is we can use these transformers, and it's a lot more flexible to move around. So then the last thing to sort of understand about all of this is there is no storage on the grid. And when as we talk about renewables, this is one of the big problems that exists within the grid. And we'll talk about things that they're doing to address it. But day to day, what goes on in the grid is whatever people are drawing in their homes and factories, however much electricity they need, the utilities have to provide the exact amount of electricity onto the grid. In other words, if there's too much electricity, if they provide too much electricity, you get into a problem, and that frequency, that 60 cycle, changes and can cause problems. So it has no storage. So the utilities' challenge is they constantly have to keep the amount of electricity they're pouring into the grid equal to the amount of electricity that we're all drawing from the grid. So that's the sort of the magic challenge of managing the grid. And we're going to see that from a local standpoint to a national standpoint as we go through the lecture. So here's another way of a graphic that's often used to depict this situation. So if the amount of electricity, the load you see coming out of this beaker or body of water, if you will, if the load is equal to the generation that's coming in on the left side, that 60 cycle energy stays the same. And by the way, at the bottom, if you look at it, the standard is 120 volts. You'll hear different things touted about, but it's 120 volts. Now you can go down to about 114 and you can go up to about 126. The devices, your stove, your oven, your hot water heater, your vacuum cleaner, your air conditioner, they're all accustomed to a certain amount of variability. But what happens is if you're generating more electricity into the grid and the load isn't there to consume it, the frequency goes up, and it goes up. And if it goes to a certain point, all of a sudden your devices will start to fail. Circuit breakers will pop and so forth, because the systems are not designed to have something that's greater than 60 cycles per second. Likewise, if you aren't generating enough and there's more load demand, then it goes below 60 cycles. And we'll see that specifically when we talk about Texas. So the balancing act is key. And that's one of the most important things that the utilities have to do. And one of the challenges of how you manage this thing. So then the other thing to talk about is, as we go through the talk, we're going to talk about, I mentioned it before, if you look at this diagram, there's the generation side of the grid, or that generating station you see in the little graphic, the stepped-up transformer, and then there's the transmission portion of the grid, where you've got the electricity up at a high voltage, and to make it economical and possible to transmit over long distances, tens of miles, hundreds of miles, different size transmission lines, and depending on how the voltage, depending on how much energy you're trying to move. And then it gets down to the distribution system, the green section, which is what we all work with or interface with in our homes and our factories. Now, there are some large factories that will take a direct transmission level customer, like that would be like an automobile manufacturing facility, or a plant that's creating, forging aluminum. Anyhow, very large energy consumers can take a direct feed from the transmission lines. But most of the world, everything in Holland, in the Holland area, is like the green, where it's a secondary customer or a primary customer that is, again, taking voltages at a lower level. So 3 parts of the system: generation, transmission, distribution. So let's talk about generation sources. So the first up is solar, and solar has become incredibly economical. in terms of land use, it's a bit of a challenge, but the biggest part of its challenge is the sun only shines certain times of the day. And so if you think about these, as we go through this talk, as you think about trying to manage the demand and the load, solar is very powerful, but it's also very much of a challenge because of its not always present. Likewise, wind is a little bit better in that the wind turbines have become very efficient. And both of these technologies, the cost factor has become very viable in terms of generation of power. But once again, if it's not windy, you aren't getting any electrical power. So the two things that are very important with renewables in these two categories is how do you store that electricity? Having effective utility storage is very important. And it's part of the development that's still required to make these truly viable on a high percentage of the electricity generation. Then there's geothermal. Geothermal takes the heat out of the crust of the earth and brings it up and allows us to turn generators. There's not a lot of it, but there's certain areas of the country where it's a viable technology, but it's pretty small in the mix, and we'll see that later in some of the charts. Hydro is a great renewable technology. In Michigan, there are 13 dams. They're small. The largest is the Croton Dam. And you'll see in the percentages in Michigan that it represents some electricity, some amount of generation, but it's not big. But it's very big out west. You talk about the dam on Lake Powell, Hoover Dam, up in the Northwest. There's lots of dams and hydroelectric power down in the Tennessee Valley Authority. Most of those big dams were built by the government, and so that energy is sold by the government. We'll talk a little bit about that as we go through the presentation. So hydro is very effective. Of course, if you've paid any attention to climate change and what's going on in Arizona and Hoover Dam, they're now to the point that Lake Mead, the water level is so low that they're now concerned about at some point not being able to generate the amount of electricity that it used to provide. Then biomass, we have examples of biomass here in Michigan. Just go east of Zeeland and the Ottawa County landfill there generates methane gas, and that methane gas is used to generate electricity. Again, not a huge volume, but definitely a source. And then gas, natural gas is sort of coming on as the biggest generator at this point. That's the Holland Energy Park, and we talk about that in more detail. That's a natural gas system, and you'll see in some of the charts, natural gas, it's a cleaner fuel than coal, but it's still a hydrocarbon and still introduces heat sealing gases into the atmosphere. So it's not a perfect solution. Nuclear, there's a lot of nuclear plants in the country, and nuclear plants are actually the cleanest form of energy generation. And unfortunately, throughout time, the society we've all been, alarmed by what happened at 3 Mile Island, what happened in Chernobyl, what happened in Fukushima, in those disasters. And so new nuclear power plants are much smaller, much safer, much more efficient, but the society is very reluctant to deploy them. But at some point, we're going to have to face the music that at this point in time, it is one of the best forms of electricity generation. And then next we have coal, fossil fuel. We'll talk a little bit about the J.H. Campbell plant between Holland and Grand Haven, a very large coal plant. And coal was a very dominant supplier of energy in our country for many, many years, but you'll see in the chart that's waning. And it's waning because natural gas has become so cost efficient, so cheap, that it just doesn't make sense anymore. And we'll talk a little bit about Consumers Power plan to close the J.H. Campbell plant. And so battery storage, as we talked about, about the renewables. Battery storage is a critical technology, and the catch with battery storage is batteries have all been focused around the automotive industry in terms of the development of batteries to make them small, to make them portable, and so forth. And the industry has come a long ways. But what's very important going forward is the development of large-scale, utility-scale batteries that can discharge energy over a long period of time. And there's some big things going on there, but there's a lot of work to be done. So those are the sources that you typically see, kind of covers the landscape of sources of electrical generation. So then transmission. I've included a little map here of some of the major transmission lines in the state of Michigan. And amazingly enough, you can kind of look at a pole and get a picture of what's going on. So you, in the right-hand side there in the top, you'll see the different some of the different configurations of transmission towers. And in particular, as it relates to Holland, the Holland Ring, which we're going to talk about more, the BPW transmission facility, the second pole from the right that's listed as 115,000 volts. That is the pole configuration that's used for the ring that's in Holland. It's 138,000 volts, but that's what the pole configuration looks like. And then there's large, massive transformers that work at these high voltages that allow you to move them up and move them down based on transmission and various distances and so forth. So I have a couple examples of those. So then the distribution network, which is really the network we all know the best because it's what comes to our homes, is taking that high voltage and with a transformer that you see in the upper left, dropping that voltage down and distributing it around our neighborhoods and to our homes. And I have pictures. We don't have time to go into all the different devices here, but there's all different devices that you see out on the poles that allow them to shape, condition, protect, and switch the energy as it goes to the distribution network and comes to our home. And so you see there on the far right, in the center, again, the two types of transformers that you typically see that come to, that is sort of the last connection to your home. And when we say grid, by the way, just a little side note, the grid generally is referred to as the transmission network up. The distribution network is generally not considered part of the grid. So then you have your home, and you have circuits in your house that have a number of outlets and lights and so forth. And there's standards for all of those in terms of how many lights you put on a circuit and how many outlets you put on a circuit and so forth. And all those cables that are in the walls of your home all move to a breaker panel. And here's an example of a 40 position breaker panel with the cover off. And so that central circuit breaker panel is how the individual lines in your neighborhood lines in your house to distribute the energy to the various locations in your house. That then is fed by electric meter. Electric meters have become more advanced nowadays. They now actually have a cellular connection, so they report back to the utility on a regular basis. So the days of meter readers are gone, and the meters can flow in either direction. So if you have solar panels on your home and you want to generate electricity and put it back on the grid, the standard electric meters now measure that. And then again, to our two favorite transformers that connect our homes. So that's sort of a sort of front to back look at what the how the electricity utilities and the grid is built. And so from there, let's now switch and talk about BPW. So the Holland Board of Public Works is a municipal owned utility, meaning it's a utility owned by the city of Holland. And we'll talk about different types of utilities later. They provide a lot of services. They provide electricity, water, wastewater, and communications. But we're just going to talk about the electric part of part of that business. So I would tell you that it's a very well managed electric utility. If you've paid any attention to this, they have modern equipment. It's well designed. It's well architected. It's very well run. And we'll talk in more detail. So we'll talk about the Holland Energy Park, how it's built, how it works. They have external sources of electricity. We'll see that. And they're delving into renewables. We'll talk about that. We'll talk about the transmission structure of the BPW as what's called a ring architecture. It's a very reliable design that's used in grids. And then we'll talk about how it interconnects to the rest of the world. We'll talk a little bit about the distribution system of BPW and how it gets electricity to your homes and to your businesses. BPW is a member of the Michigan Public Power Agency. It's a group of municipal utilities. It allows them to buy with a greater presence in the marketplace because they're buying as a combined entity. And some of the work that we'll see they've done has been through the Michigan Public Power Agency. So the Holland Energy Park, it's a very cool design, very modern, went online in 2017, great architecture and great engineering. And so we're going to talk about, we're going to be talking about that large building and what's in it and how it generates electricity. So several steps here. So the first step is there are two main generators. They are combustion turbine generators. I call them, they're basically a jet engine that's bolted to the floor. And they each generate about 50 megawatts of energy. This is the generator over on one side. These are the air intakes in the top. And so the engine, if you will, is right here. And if you look up above, this is kind of what it looks like inside. So the air intake comes in here. You see these fan blades. And the fan blades, as it rotates, it compresses the air. And as the air is compressed, you combine it with natural gas. And once combined with natural gas, it's ignited and drives the rotation of this thing. And so the generator is attached back here at the shaft, and the flames are inside the unit, and hot air, very hot air, comes out the end. But again, it's a jet engine bolted to the ground that's turning the generator. So, but we don't want to take all that hot gas and just waste it and send it out. So then there's an enormous thing, and these, I don't have these quite scaled to size. This is probably another third the size of what it is compared to this. This is enormous. Like a person standing would maybe be about that tall. So what it is let's take that hot air that's coming out of that jet engine and get more energy out of it. And so what they do is they pump water into this thing. And so in these lines in here, and that water is heated up, and that warm water then comes into an evaporator that turns it into steam. That steam is then taken and superheated to get it up to a much higher pressure. And then that is piped out of this exchanger and over to this generator that takes, basically they're using the hot air coming from this jet engine and using it to generate another 45 megawatts. This is what's called a combined cycle gas generating system. It's incredibly efficient. If you think about the old, I apologize, I can't remember the name of the old coal-fired plant. It had about a 25% the energy that went into it, the BTUs of that energy was about 25% level of efficiency to get it to electricity. This system is about 60%. So it's much more efficient. So then it takes that hot water after it's been run through this generator. Actually, there's an exchange process, and that hot water is taken out to one of these, to this cooling tower. There are 3 units. And that cooling tower, that water comes into the top. It's sprayed over air that's pulled in by a fan. And it's sort of like if you think of yourself coming out of the Lake Michigan or a swimming pool, and it's kind of a breeze that day and you feel cold. Well, that's the exact same process that's going on here. So that water is sprayed over that air, it cools, collects at the bottom, and is sent back into the plant. Also, we'll talk a little bit about snowmelt. The green pipes represent the connections of the cooling tower to snowmelt. So looking at it sort of graphically all put together, you see the two generators here in the center up at the top, and they're being driven by this jet engine and the fan blade you see here, air is coming in and whatnot. And so the hot air that's coming out of the jet engines is then taking that cold water, turning it into steam, and that steam comes over to this generator, to this third generator that generates electricity. So that steam then dissipates, comes back to water, but there's another loop that goes through this exchanger that goes out to the cooling tower and out to snowmelt and out to the streets. So again, taking the heat from these two jet engines and using it to warm the streets in snowmelt for the wintertime. So, and then one, I had said that it was, let's see, let me go back a minute here. Plume abated. So if you paid attention over the last several years, probably 10 years, it's been a while, the generator that was the power station that was built on the east side of Zeeland, they had a lot of problem with plumes of air coming out of their cooling towers. And I can't remember the number of the street, but the street was impassable. They finally put up gates to close down the street when that plume was created. And so BPW was very wise, and they had a cooling tower that was designed to minimize the amount of plume. And so that's why it's called a plume abated cooling tower, so they wouldn't have that issue. So once you go through all that, there's a couple of pictures on the outside. So this is the backside of the power plant. So again, you can see the air louvers for coming into the jet engines. And then you can see you don't really call them smokestacks because they don't emit smoke. It's just hot air that comes from those two jet engines after we've taken the heat and gotten as much electricity, much energy out of that heat as possible. If you turn around here and look to the north of the rear of the power plant, you'll see three of those large transformers we talked about earlier. So the energy comes out of the generators at 13,800 volts, and these transformers crank it up to 138,000 volts, and off it goes to the transmission environment. And you can see, remember we talked about three phases. So each of these is the cables that are coming out from the three generators, and notice they're broken into three groups, which are the three phases. Out of the transformers come the three phases. These buses allow them to combine it together, and then out onto the grid, out to the transmission environment, there's 1, 2, 3 phases of the wires that go out into the ring. So that's a little bit about Holland Energy Park and how it works, but that's not all. So if you look at all the BPW sources, the yellow up at the top are the three sets of generators that are owned by BPW. The Holland Energy Park and the three generators are represented by the first line. And you see it has a total capacity of 145 megawatts, of which BPW owns it, so they have it all. Down on 48th Street between Hayworth and the ice cream place, there's, Hudsonville Ice Cream. There's a generation facility that's basically outside. It's what's called a peaker plant, and we'll talk about that later. It deals with when there's a peak energy demand, like this time of day when it's hot and everybody's running their air conditioning and factories are running and so forth. They have an additional 160 megawatts of energy that they can generate from that location, not as efficiently as the Holland Energy Park, but it's available. And so that's an additional facility. And then on 6th Street, there's an old installation, a small oil-driven generator that is pretty small. That's getting to the point of being end of life, of not being practical, because in all of this, you always have to understand how much, what dollar does it cost me to generate electricity? How efficient and how cost effective are these systems? And 6th Street is getting towards the end of its life, but it's still there and it works. So then the rest, everything else in this chart is all purchased from others. So the two orange lines talk about the commitment to a contracted amount of energy. You can see from the J.H. Campbell, there's 3 coal units there. One of them it's actually unit number 3 that has a 770 megawatt capacity. BPW has a contract with consumers for 10.4 megawatts coming out of that plant. And then there's a coal-fired plant over on the east side of the state. Again, a large plant from one of their units that BPW has a 35.6 megawatt contract for that energy. So those are 2 coal-fired plants. Then everything else you see on the list are all renewables. So you can see wind, the wind installations. I have the number of windmills at those installations. You can see the size of those installations, and you can see that BPW is, in other words, this BB wind farm down in Ithaca has an 81 megawatt capacity, and BPW has a contract for 16 megawatts. While in Gratiot County, they have a 15 megawatt contract, and so forth. Then a couple of the natural gas, not the one east of Zealand, but other locations, they have a small commitment. And then solar in Michigan is not the greatest, but there's new solar installations that are being built, and that's why you see the dates here are much more recent. And you can see that BPW has commitments. They have one that's in place today for Shiawassee County, and one that's in place today from Calhoun County, and then they have others that they've committed to. So if you look at the theoretical capacity BPW has available to it, if all the sun was shining and all the wind was blowing and everything was running, a total of 443 megawatts of capacity, a lot of capacity. But the fact remains is that's not all available at the same time. So let's keep going. So here's the decision that they have to make. So with all of this, the BPW, there's an individual that's running every shift that's making decisions. And so what happens is, if you see on the right-hand side of or left-hand side of the diagram, there's a demand forecast. All utilities forecast their demand. They look at what's the next day going to look like and what's the next week going to look like. They do longer term forecasts, but that's kind of the dynamic nature of what's it look like? What's the weather look like? What time of year is it? And so forth. And we'll see some of these demand curves later. So they have a forecast. They also have an internal generation capability we've seen of 328 megawatts. But each of those 3 types has a particular cost related to it. And is that generator, is it down for maintenance? Because you have to do maintenance on these things and so forth. So you have to understand the availability. You have to understand what systems and what their effective cost is. So then they also they have these purchase agreements with these other providers for a total of about 115 megawatts, but they have a cost related to them as well. And they have availability issues as well. So is the wind blowing? Is it sunny? What kind of maintenance is going on in those facilities? So they have to factor all of that in as well. And then we'll see later, there's a dynamic open market. It's almost a commodities type operation that allows them to buy electricity on the open market for a given price, typically a higher price, certainly higher than what they can do on their own, and most likely higher than what's in than their contracted providers they have. But at the same time, if the open market, if the price is good, they can turn around and sell the electricity they generate to others. So the person in this role is saying, what is the demand that we have that we need to provide for? What can we provide it for? What cost? What's available from our providers? And or is there a better, am I better off to take this, and what typically happens is they typically generate their own electricity from their facilities. And when they don't need it, they'll turn around and sell this contracted electricity, if the price is right, to other operators and make money. So if you listen or look at the BPW things, publications, newspaper articles, their annual report, you'll see that in fact, it's been publicized that they're paying off the bonds faster than they had planned on, because they're being able to make more money by selling energy to other operators, typically from these external contracted providers. Because they have enough capacity internally, they can sell it and turn around and make money. And so they're paying off the energy park faster than what they originally projected, because they're making more money out on the market. So that kind of gives you a little picture of what's going on with BPW and the utility that we all, we're on the north side, so we're Consumers Power, but we just have a great example of a utility in our town. So let's talk about the transmission ring. So the transmission ring, you can see up the northernmost portion of it is on Quincy Street. There's a substation up here at the on the west side of 31. It comes on down kind of through along the railroad line that goes up to the coal-fired power plant. There's a substation here. It goes down 120th. There's a substation out here to a more rural area. It comes over to Lakewood and the water tower, and that's the interface to the grid. We'll talk about that a little later. Down here by Lake Makatawa is the Holland Energy Park. And we saw how those transformers get to that line, and that line comes up onto James Street and it gets inserted into the ring. And this is, again, the northern view of the ring. There's a southern portion. The southern portion, we'll look at this particular substation down by the old power plant. And then there's one, many of you, if you get out on 196 to go south, or 131 and so forth, you'll see a substation there just by the exit. Over here, there's the peaker units for generating electricity when there's peak demand. And then there's one substation way to the south. So that's the transmission ring. Energy is flowing in either direction. Depending on where the generation, where the power is coming from and where the demand is, the physics of it is that it goes as close as possible to the source, to the load. And so that's part of the idea behind the ring, is the electricity can flow in either direction. And if one connection to a substation fails, the energy can come in the other way. So it's a very well-designed system. So distribution. There's 9 substations we've seen on the 24-mile transmission loop. Substations convert that 138,000 volt system for distribution. The distribution circuits they're basically 7,200 volts, but depending how you configure it, you can get 1,200 volts out of it. And they generally connect 10 to 12 circuits that might be in the air or in the ground that distribute out to the homes and businesses. The distribution network consists of about 600 circuit miles, and they currently serve about 300 customers. And so I included this picture of the substation by the old DeYoung plant. Sorry, that was J.H. DeYoung, or I can't remember the initials, but DeYoung, the DeYoung plant. So this substation was built to replace the one that was there. So here you see the 3 phases again coming in from the loop. Coming in through these circuit breakers and switchgear. You can also see the 3 phases going back out to the loop to continue on. It goes through this various switchgear and circuit breakers and so forth. And you see these 2 transformers. And this is a very standard, all their substations look the same. So there's these two transformers. And then there's a setup here of each of the circuits exits the station. In this case, they all are underground. And so here's a circuit, here's a circuit, here's a circuit that go out to feed the Padnos, to feed downtown, Donnelly's, that's not Donnelly, but anyhow, the various factories and so forth in the area that are served by this substation. All their substations have a very similar design. It's all very standardized and well designed. And so that's an example of how the energy gets off that transmission and out to the distribution, out to our homes and businesses. So then how does it connect to the grid? Well, where that connection occurs, and this picture isn't of the place because I wasn't going to go around and take pictures and have somebody go, what's he doing? But this is an example of a substation, and it is at the corner of Lakewood and 112th. And so that loop, the transmission loop that we talked about, comes in and goes out, if you will. And then there's 4 lines that come in from other parts of the grid. There's 238,000 volts lines that come in from various parts to the south. There's 1 dedicated line that comes from the J.H. Campbell plant. And then there's another line that comes from elsewhere in the grid. This substation is owned, it's called the Black River Substation. It's owned by the Michigan Electric Transmission Company, which is a subsidiary of ITC that owns many transmission facilities. This substation was originally built by Consumers Power and was owned by Consumers Power. But as we'll see in the history of the evolution of the grid, all the transmission systems were basically vertical utilities got broken apart. And so now there's several transmission companies that own the transmission part of the network. So anyhow, that's how BPW connects to the rest of the world. So that's an overview of BPW. So now let's kind of look a little bit at the rest of Michigan. So there's investor-owned utilities. So those are publicly traded companies, and Consumers Energy and DTE are both investor-owned companies. There's cooperatives. Those tend to be in the rural areas where a bunch of communities will get together and form a company, a cooperative that's owned by the various communities that provides electricity in the rural areas. There's municipal utilities, of which BPW is one. We'll talk a little bit about the fuel mix of what's powering the energy in the state of Michigan right now. And then I put together a little slide because of the recent announcement with Consumers Energy, talk a little bit about that. So not going to go into detail here, but this is the non-municipal electric utilities in providers in Michigan. That's Dave Koester made sure I put in non-municipal. Anyhow, so the sort of mustard yellow in the center is Consumers Energy territory. The sort of turquoise blue on our east side of the state is DTE's territory. And this is electric. So these companies have gas and other utilities. So this is just the electric system. And then you see in the southwest portion of the lake of the state, you'll see the Indiana Michigan Power Company is kind of the orange there. And then up in the UP, there's various different utilities. So, but anyhow, this kind of gives you a view of what the utility service areas look like in the state of Michigan. These are the various cooperatives that cover various territories of the state. Again, not going to go into details, but just you can kind of see they typically are more around the rural areas. And then these are the municipal providers. Every star represents a municipal system. There are 40 municipal electric utilities in the state. They serve about 300,000 customers. The largest is Lansing at 100,000 customers. The smallest is Daggett with 200 customers. Holland BPW is the second largest, both in number of customers and demand. So it's again, a significant system within the rest. There's one in Grand Haven. There's, they're all over. So anyhow, those are the municipal folks. Here's where our energy comes from in this state. So coal is still the predominant, although that's quickly changing at whatever, I can't remember, 33% or thereabouts. Natural gas is about 31%. Nuclear still is running at about 28%. The non-hydro renewables, which there's a second chart there, you can see that runs about 7%. Those 13 dams that I mentioned, they represent a little over 1%, and oil is still there in a few small installations at about 0.5%. So if you look on the lower right, you'll see the non-hydro resources, that wind is about 5.5%. Biofuel is hanging around 1%. Biomass is under 1%. And then there's a little bit of wood, there's a little bit of solar, and there's even some solid waste. But again, it doesn't even register on the chart. So this is the demand, or this is the sources of energy for the last 12 months ending last July. So that was the most recent data that I could get. I suspect they're going to publish updated information at the next month or so, but that kind of gives you a picture of where the energy sources are at this point in time. So I wanted to put a quick slide up about consumers because of the recent announcement of and it's an offer. It hasn't been approved yet. We're going to talk about regulation in a little bit. It has to be approved, but they've proposed to close the J.H. Campbell plant, which is a coal-fired plant, and the D.E. Carn facility in Bay City, Michigan. As you can see, both of those are large plants, the orange down here. But you can also see they own the Zeeland power plant that was actually originally built by Merritt. Merritt went out of business. They went bankrupt, and consumers bought that generation utility. And so then you can see there's a lot of wind and hydro, and they're planning on buying several other natural gas facilities around the state. You'll notice that if you look at the total, they would be shuttering about 3,000 megawatts, and they're buying about 2,000 megawatts. So there's still more to happen. But the key is the Michigan Public Utilities Commission has to approve this. So they proposed it, and there's some implications that we can, I can go into more details, but don't have the time. There's good and bad to this. And there's good in terms of from a pollution standpoint. There's some bad as it has to do with rates. And so we can talk about that if people have questions later. So let's talk about the national grid. We'll talk about the history, region, and talk about regulations, and then we'll get into a management section. So the history. So the first utility with this was Thomas Edison. Thomas Edison was a DC voltage advocate. He built a generation facility on Pearl Street in New York City. Had about 85 customers. They measured things because they didn't have anything else at the time. He measured it in 85 customers with 400 lamps. Then he installed a much larger generator in that facility as they learned more and got perfected things. So they got up to 500 customers and about 10,000 lamps. And so then what you had on the East Coast, several more DC systems were built in sort of major metropolitan areas. And then if you want to have fun, there's a great movie called The Current Wars. It's only a couple years old, and it talks about the competition between Edison and Westinghouse. And behind Westinghouse was an individual by the name of Nikola Tesla. Nikola Tesla was the father and the thought behind AC. And whereas Edison was a DC guy. Well, the problem with these generation stations, they could only get the electricity to go at about a mile, and after that it would dissipate and wouldn't work. And so it had very limited viability. So he had this vision of building electrical generation plants all over the place, and it just wasn't practical. Well, Tesla had perfected AC, and so there was a huge battle between these two guys. And Tesla got aligned with Westinghouse, and they built the Niagara Falls AC system. Was installed. They started the construction and brought it online in 1895, and then they expanded it several times. And there they transmitted that electricity because it was AC. They could now go many miles, tens of miles, hundreds of miles from that facility. And it became, all of a sudden, it just became a very viable technology. These two guys were interested. Edison did a lot of wonderful things. He wasn't necessarily a nice guy. And Tesla, he was a very kind of an odd individual, an incredible brain, terrible business sense. Anyhow, if you want to have fun, watch that movie. It's very interesting. So anyhow, private electric companies grew, some cases duplicating services in large cities. And I just included this. Here's an example of what this, I don't know which city this was. This is an actual picture on the right. And this is a drawing on the left. But what happened is as they started building these utilities, to your given house or apartment, you had 3 or 4 different electrical choices, companies that you could buy electricity from. It just wasn't practical. And so private companies grew, duplicating services. And then in New York in 1907, Commonwealth was the first one to consolidate power companies so you didn't have all the duplication. And what people realized was these things are going to have to be monopolies, if you will, to an extent. And so states formed regulatory commissions to make sure that these monopolies weren't abusing their privilege, if you will, and not charging exorbitant prices for what they were providing. So that's sort of the beginning of the regulatory environment, because it just wasn't practical to have so much competition. Then in 1935, as they started expanding, and you could now have interstate financial transactions of transmission going between states, and to buy and sell electricity, state regulatory organizations, that wasn't good enough at that point in time. So that's when the federal government got into the regulation of electricity to make sure people weren't abusing the situation between the various states. And this is where Texas, in all their infinite wisdom, said, we want to be different, and we don't want to be regulated. We don't want the government in our business. And so we're going to do it differently. And so we'll see as we go through the various slides how that happened. So then in the 60s, it became much more economical to make electricity. And so it grew a lot, and then transmission became much more possible as they got high capacity transmission lines, transformers got more sophisticated, and so forth. Then, and I'm not going to go into all of these, but in the 90s, there was an effort to see how can we make this a more competitive environment. And the upshot of that was that what used to be vertical utilities, in many cases, they had separate companies that owned generation facilities, other companies that owned transmission facilities, and other companies that own distribution facilities. And through that, and again, lots of different regulations that have occurred and subsequent to that to make that as viable as possible. So that's sort of the history of how it evolved. So how this evolved in terms of a structure is there's an eastern and a western grid. There's a major interconnection. They're called interconnections. There's 8, the eastern grid is 8 regional councils. There's 32 load balancing authorities. And the total electrical capacity of the eastern grid is about 650 gigawatts in the winter. And because of air conditioning and whatnot, in the summer, it's about 750 gigawatts. The western grid is about has 37 balancing authorities, but it only has about 125 gigawatts in the winter and about 150 in the summer. So it's much, in terms of amount of energy, it's much smaller than the eastern grid. And then we have Texas. So Texas wanted to be different. They didn't want to be regulated, so they set up their own grid. So they have one balancing authority, and the Electric Reliability Council of Texas. My snide remark is reliability is a questionable name in their questionable part of their name, but they have about a 65 gigawatt demand in the winter and about a 75 gigawatt demand in the summer. They serve about 60% of the land area and about 90% of the consumption. Now there's a separate interconnect in Quebec and Alaska. We're not going to talk about those, but there's other interconnects in parts of North America. So this is what it looks like. So the blue is the eastern grid, the red is the western grid, and then you have Texas on its own. And so if we go back to the 60 cycles, what that means is each one of those grids, the 60 cycles that you get in Holland, Michigan, and the 60 cycles that you get in Miami, Florida, if you were to map those, they would be totally synchronous with one another. When it went to 0 in Michigan, it went to 0 in Florida. They're all synchronized in that blue area. Likewise, in the red area, they're all synchronized. And so that 60 cycle, they're each independent synchronous grids, and they run the 60 cycles. They aren't necessarily timed the same as the 60 cycles, but that whole geographic area is all running that same 60 cycle set of energy. That's a huge coordinating effort. And then you've got Texas down with their own. And so they have their own 60 cycle grid that's separate. So, and there's interconnections, and the interconnections are connecting those 60 cycle networks. If you go back to our first slide, they're DC interconnections. So they convert that AC to DC, let's say in Rapid City, they convert the 60 cycle AC connection of the eastern grid, they convert it to DC, and then reconvert it back to the 60 cycles in the west side. So the 60 cycles don't have to be the same, but they have these various interconnections. And these are large interconnections. You can move a lot of energy across them. You'll see Texas only has 2. And by the way, they're very small, because if they would be large and if they were doing transactions, they would have to be regulated by FERC and the federal regulation entity. And Texas didn't want to have that. So they have a couple DC connections, but they're just very small. Which also means, by the way, when they failed, they didn't have the opportunity to import electricity to bail them out. And so that further aggravated the situation that happened in Texas. So anyhow, that's what North America looks like. Again, I just thought I'd throw in a slide to sort of exemplify the difference in the size of these respective grids in terms of the amount of energy that they manage, or that exists on that grid. So there's about 7,000 power plants, about 160,000 miles of transmission lines, and in terms of actual customers, it's about 15 million customers. So that's a little bit about the size of grid. So let's talk about regulation. So there's a lot of agencies, but there's 3 that really matter. There's 2 at the national level and 1 many at the state level. So FERC is the Federal Energy Regulatory Commission, and NERC is the North American Electric Reliability Corporation, FERC and NERC. There's others. If you have a nuclear power plant, NRC is involved, EPA for pollution and so forth. But in terms of what's really managing the electricity and what's going on, it's FERC and NERC. And then the states, they have public utility commissions that are all holdover from back in that early history of the grid, to make sure that utilities that we as citizens get charged reasonable rates. So the FERC it regulates interstate commerce. So anytime energy is being sold across state lines, whether it's in the eastern or western grid, they're responsible. They have very limited regulation of in-state Texas grid because Texas designed it that way. So you basically can't do any sort of significant transactions across states. And so therefore they don't have to be regulated by the feds. Transmission of power to interstate commerce by public utilities. They review mergers and acquisitions. They license anything having to do with hydroelectric projects. The federal government is responsible. They mandatory reliability standards. We're going to talk more about that. They monitor the electricity markets. We're going to see some of that. They handle some of the accounting and so forth. And then anything that occurs at an international border, they're responsible for. And then, because I mentioned most of the dams were built federally many years ago, they are selling the electricity to the public, and so FERC is responsible for making sure that's priced right and they follow the rules, etc. So NERC, they were formed after the 1965 blackout. I'm suspecting that most of the people on this call would remember that started in New York. And it was at that point in time that a number of the utilities voluntarily got together, and engineers from various utilities got together and said, we need to start setting standards. And so, through some of those regulation changes in the 90s and so forth, this organization moved from being a voluntary to being one that sets the standards and audits the standards. So their goals are to develop and enforce reliability standards in terms of how things are designed, how things are operated, what sort of maintenance. Like, and a perfect example of maintenance is tree trimming around power lines. You see that locally, but when you talk about large transmission lines, it's a big deal. Trees are a big deal. And by the way, on on the north side of town, trees are a really big deal. We actually have a full house generator because of trees. But anyhow, another topic. Anyhow, annually they assess a seasonal long-term reliability. BPW has to go through an audit every year. And one of the things they say they have those generation facilities we identified have that ability to produce that much energy. They have to prove it. And if they can't prove it, then because they have to be able to demonstrate that they either can generate or can buy enough energy and have a buffer to make sure they can serve our needs. By the way, there's no buffer in Texas. They don't care about that. And we'll talk about that in a little bit. So they get, NERC is responsible for assessing long-term reliability. They monitor the bulk buying of power. They establish rules for wholesale purchasing. They establish rules for generators. And they have a tremendous education, training, and certification facility for industry personnel. And I just threw in this graphic down the bottom. If you look down in the lower level here, they have rules for transmission ownership, for transmission operation. They have have rules for generator operation ownership, what rules follow there, and operations and so forth. So they have a lot of different rules and things you have to follow to make sure that we as a society have reliable electricity. So then the public utility commissions, and the biggest thing with the public utility commissions is the rates that they charge people, the utility charges people. So in the state, they regulate retail sales. They regulate where generation and transmission, where facilities are built. And the states vary. Some have different, some are more, have tighter regulations, some have more deregulation. It varies from state to state. In our state, it's the Michigan Public Service Commission. They regulate 8 privately owned electric utilities, of which Consumers and DTE, and that Indiana, Michigan are the 3 largest. They provide basic oversight of regulated cooperatives, of regulating cooperatives. Again, they don't have to, in the case of cooperatives, in the case of municipal owned utilities, in our case, the city council is the one that's making sure that BPW has competitive rates. And the whole reason BPW exists is to be able to generate electricity and have a lower rate. And so the state doesn't feel that the public utility commissions don't have to regulate the cooperatives and the municipalities because their owners are, the whole reason they exist is to have competitive rates. So that's why it's a little different. So let's talk about management of the grid. We'll talk about a little bit about reliability. We'll talk about demand. Let's look at some diagrams of the network, talk about generation and then how they manage it. So NERC has these companies or organizations that are responsible for making sure that the reliability standards are followed. And so Michigan falls under the RFC, so the Reliability First Corporation. They're the ones that administer the standards and verify that people are following those standards. And there's big time fines if you aren't following the standards. So there's plenty of motivation to make sure things are done right. So let's talk a little bit about demand. So this is just an example of 24 hours in the day and what electricity demand might look like in a particular utility. So the first thing, that lower blue, is what they call base load. And so the base load it's the demand that's always, the energy demand that's always going to be there. Don't have to, it doesn't vary. And so I've got to have generation capacity to cover my base load. And so, for example, examples, a nuclear power plant are one of the best designed generators for base load because they're very constant, they're very consistent, they don't vary a lot. Then there's an intermediate load that is pretty typical, but it can vary a little bit. And then there's the peak. And the peak is when we're all awake. It's when we might be running air conditioning. It's during the prime time of the day. And then the green at the top is operating reserves. And so everybody has to have sufficient reserves. That is one of the big byproducts of regulation. Not so much in Texas, but in most of the utilities. So then here's another way to look at demand during the day, during time of year. So the spring is pretty consistent in terms of, it's lower at night, but pretty consistent during the day. In the fall, as it gets colder, you can have greater variability because you're heating and you might have some hot days and so forth. Winter, you can see the humps in winter when people get up in the morning and they go to work and then they come home at night. And so you get kind of a peak early in the morning, you get a peak early in the evening. And then summer is always the high point because summer is when the sun is shining. It's when it's the hottest. It's when we as human beings want air conditioning running. And so that's when there's the greatest demand. And so that's it kind of gives you a feel for how it can vary during the course of the year. So then let's talk about how we might solve that. So this is just an example from a particular part of the country. I believe it's in the Northeast, but I'm not sure, it doesn't matter. So in this particular scenario, the green at the bottom represents the nuclear capabilities of this particular utility and how they're covering the base load there. Then you see the darker blue is the next level up is natural gas and how it can vary and so forth based on availability of their systems. Then you see blue, that's why I think this is in the Northeast because it has a big hydro component throughout the day. And so that's very consistent. And then they're importing a lot of electricity. So that light blue, you can see that varies throughout the day as how much electricity they're buying from others. Then this one has a fair amount of biomass. You can see that gray band is pretty consistent. That source doesn't vary much. Then you'll see orange is the wind. And so I don't know if this is an average over time, but how the wind might vary during the course of the day. And then you see solar. And solar is wonderful when the sun's shining, and you can see how much of that demand that it makes up. And the dotted line represents the demand or the energy that's being consumed by the public. But then you see red, because there's so much solar, there's excess renewables. So what do you do about that? So you can crank down the other sources, but wouldn't you like to be able to store that and be able to use it later? And that's the challenge. And that's why batteries are such a big deal. But anyhow, just a kind of an example of how different sources of generation can be used to supply the needs. And then I put this one in here because so we all now understand that the utilities are having to balance the stuff, and as more demand comes up, they got to crank up the electricity. If demand goes down, they have to crank it down. So these on the left, you see a table of all the different types of generation facilities. Then the first column shows you of that generation facility, what is the minimum amount of energy that can come out of that generator? So what's the lowest they can go? So for example, and you see a nuclear power plant, it can't run than less than 50% power. A gas turbine combined cycle, the Holland Energy, they can go less than about 20%. Then how quickly can you change it? That's what the next column tells you, is what percentage of the capacity of that generation facility, how much can you move it in a given amount of time? So nuclear, you can only change the volume by 2% each minute, not very much. Whereas the gas turbine combined cycle, you can move it quite quickly, and you can go up or down by 20% in a minute. So the point in all of this, and then the last column says if the thing is ready to go from zero to full bore, how long does it take? Well, a nuclear power plant takes a whole day to get up to speed. A coal plant takes about 3 hours. And so the point in all of this is the balancing act the utility has to take, is as we all turn things on and turn things off and the demand varies and goes up and down, they have to deal with these constraints based on the mix of energy that they have. And so they can't just, the point is they can't just turn it on a dime. And so that's the complexity and the challenge of what it takes to manage that power generation. So a quick look at what the US looks like. So in the chart in the upper left, you can see where coal peaked out at about maybe 2006, 2007, and it's dropping very quickly. And you can see gas is the orange is filling the void. You can see petroleum, that sort of brownish color, has become very negligible over the years. Nuclear grew a lot, and it's staying pretty consistent. Hydro, the hydroelectric, the dams and so forth, again, pretty consistent. Biomass is not a lot. Geothermal is not a lot. But you can see wind's now coming on strong and solar is starting to come. But it's a long ways to go, and batteries are the key to making that happen. So another way to look at this, if you just look in 2020, 40% of our country, the grid was powered by natural gas, 19% down to 19% for coal. Nuclear is holding at about 20%. Petroleum was negligible, and renewables are about 20%, of which 8% was wind, dams were 7%, solar is only 2.3%, and the others are sort of negligible. So if you want to see where we are as a country right now, this kind of gives you a picture. And utility scale batteries. And so I've mentioned this many times. These are a couple of installations, but there's a lot of work to be done here. Again, the focus on cars has made us, battery technology has come a long ways, but for use in utilities, there's still a long ways to go. This is what the transmission lines look coming through the country. And you can see it's much denser in the east than it is in the west. And this is the generators in the country. The blue are natural gas. The black with a diamond is nuclear. And if you look out here, you'll see sun. The orange with a sunburst in the middle is solar. So anyhow, you can see there's about 7,000 power plants around the country. So as the grid got larger, and this balancing act had to continue, there had to be a higher level of organization to sort of oversee and manage what was going on. So they divvied up the country. And so ISOs, which is the independent system operators, they operate the grid in their region. They manage the wholesale electricity markets, and they do bulk reliability planning and say, hey, we need a transmission line here. We need to do this, need to do that. So they're overseeing that. And we are part of MISO, which is the I think it's Midwest Interconnect system operator. We'll talk more about that. And then RTOs do the same thing for the transmission network. So while ISO looks at the whole picture, RTOs they focus on the transmission network and how electricity is moved from one utility to another. So a quick thing about energy markets. So I've talked to you about how BPW has these contracts in place. So in 1996, the open access transmission tariff, one of the tariffs that went through, I showed you the several that was in 96. And that basically said the transmission facilities need to be separated and people need to be able to buy time to move electricity on the transmission system. So the transmission, like Consumers Transmission, their transmission facilities were sold to others and they're now independently operated. So, and they built a computer system, a internet-based computer system that allows you to reserve time and say, I want to move 20 megawatts from Ohio to Minneapolis, Minnesota tomorrow noon for 2 hours. And so you can book the time if there's an available transmission facility to move that energy. And then the ISO, in our case, the Mid-Continent Independent System Operator, they manage the buying and selling electricity, the on-demand stuff, for our region, and each region has their own. They have their own computer system, and basically you look in terms of, in this sort of energy market, if you will, you buy things a day ahead or in hours, but they give you 5-minute views of where the demand is. And I took a couple pictures. This is what the MISO looked like. This was last Thursday on the left. And so you can see that most of the regions in MISO are in the $35 per megawatt hour. And it was pretty consistent. However, up in North Dakota, there's a bunch of wind energy, and somebody had a transmission line down or something was going on, and this energy couldn't get out. And so for that reason, Minnesota was short. And so they were paying more. If you could offer up electricity, you could make another $14 per megawatt hour if you could get it to them. So this is what they were paying at the time. So then I took another picture yesterday during the day. It was 4:30 in the afternoon. And sorry, this was Saturday, I can't remember, whatever, a couple days ago. And so it was sunny out. So people are running their air conditioners, and notice how the prices of energy are much higher now around the grid. You can see there's some trouble down here. Some electricity is getting hard to move. And so Arkansas hub was, they were up to $74. So it was a premium of $21 per megawatt hour in this case versus Texas. And that's, Texas is, like you can see, it's just the edges where ERCOT doesn't exist. But anyhow, you can see it's very dynamic. And so when you start going beyond those contracted hours and energy that you have from different sources, when you go on the open market, you can sell it. And so this is part of that BPW deal, is when they see the Michigan hub is offering $52 an hour, a megawatt hour, and we can generate it internally, or they have contracted power that's $30 an hour or whatever, they'll turn around and sell it and make $20 a megawatt hour. And so it's a very dynamic thing that exists in terms of the energy markets. So because of all this, you need balancing authorities. And I mentioned earlier, the Eastern Grid has 32 balancing authorities. And you can see MISO is one of the largest. JPM is actually the largest that's over in the Pennsylvania region. But you can see some of these balancing authorities have small areas that they cover. Some are larger. But that's the entity, that's a part of the MISO group. One of their jobs is to balance the demand across the grid. So what's it mean? What's it take? Well, so this slide sort of tells you the whole picture. So at these central balancing organizations, they constantly do scenario modeling. What happens if this generator goes down? What happens if this transmission line goes down? Everybody always has a requirement that you need to be able to run your utility if something, no matter what it is broken. And so they model scenarios for different possibilities. And then they project the demands based on weather, storms, sun, cold, all those things. And so all those are factored in. So these are the things that can go wrong. That 60 cycle thing, you got to keep it in balance. And so constantly keeping the generation and load in balance. You can have weather. So in the Eastern Grid, you could have a storm, have a hurricane coming up Florida and through the residual through the southeastern states, and you have to deal with that. Or a generator can trip offline for what, it's like a circuit breaker popping, and who knows what reason, but it can happen and you have to deal with it. Or you have some situation and it starts rippling effect through the transmission lines, and you have to deal with that. Or a transformer fails, or anything fails, and that creates instability, and so they have to deal with that. And then markets, people are buying and selling this electricity. Well, can I move it from Ohio to Michigan? Is there enough capacity? What are these people doing? And what am I going to do to be able to handle it? And then the last thing is solar magnetic disturbances can cause, and this doesn't happen often. We've had quite a few years, about 10 years without anything major happening, but that can wreak havoc with the equipment on the grid. So these are all things that you have to deal with. And so then these are the tools that they have to deal with it. So let's say that there's a huge demand. I've got it balanced, but there's more demand in Ohio, and in Illinois, they're doing a lot of the generation that's being drawn into Ohio. Well, so I might cause people in Ohio to start cranking their generators up higher and tell the folks in Illinois to crank their generators down to balance the electricity so it's going as close as possible to where the demand is. I might reconfigure the grid. I might turn off a transmission line, or maybe the transmission line is failed, and I have to reconfigure things to get that energy to move around where the problem is. Load management programs. We as citizens, they will often offer, hey, we'll put this device in your house that will control your air conditioner. And so we might turn off your air conditioner for 4 hours, or your hot water heater if you have an electric hot water heater. So those are load management programs. When you participate in those are controlled by a computer system. So the folks in the control centers can say, hey, kick this in because we have too much demand and we can't manage it. Or I can reduce the voltage. I can crank it down. And we saw the ranges to keep those frequencies in balance. And the devices are all designed to deal with that. So that's another tool. They can make public appeals. We've seen that happen before. It comes out and says, hey, don't, cut back your demand because we're in a problem time here and we need you to back off. Or the last hope is instituting rotating blackouts. We saw that happen in Texas. But all this is dependent on effective planning and forecasting and being ready for what might come at you. And the final thing is do nothing. Some small perturbations occur and they might not last. And so part of the thing in these control centers is how quickly they react, because certain things might level off. And so they might take a minute or two before, given the particular situation, and see if it settles down. So that's actually a viable alternative. So with all that, the last piece here is what happened to Texas. And so we talked a little bit about Texas and regulation, talked about ERCOT, and what I would describe as a laissez-faire regulation strategy. So from the very beginning, Texas resisted all regulation from FERC and NERC. And you can see how they built the utility was based on that. The very casual regulation. ERCOT doesn't have a lot of teeth. It's getting a lot more teeth now because they're all scrambling after 200 people were killed. It was a free market system. So it's all about what's the cheapest cost of electricity, and don't worry about having extra capacity. Just get it to us as cheap as possible. So they had a weather outage in February 2011. There were extensive recommendations. FERC wrote a report. I have a copy of the report. NERC wrote a report, about 120 pages of recommendations. Said you need to weatherize your facilities. You need to weatherize your generation facilities, fuel supplies, the gear and the switch gear in the stations. And they were warned. They said, if you don't do this, it's going to happen again. And they didn't do it because it would have cost money and they didn't want to raise the rates. And so they had little focus on reliability. The pricing was for delivery of electricity. You get paid if you deliver electricity. If you don't deliver electricity, you don't get paid in Texas. And so there's no thought for provisional capacity. And they did poor capacity planning. They didn't plan properly, and it bit them. And then they didn't, their network structure. So I talked before about these distribution circuits. Distribution circuits, knowing that you have the important public services, hospitals, police stations, is a utility. You know which circuits out of those substations you need to keep them going. You don't want to roll those on a rolling blackout because that's public safety. Well, what they didn't think about in Texas is a lot of their plants run from gas coming out of wells, natural gas coming out of wells, which in this case are in Texas, and they're on the grid as well. And so there were certain distribution circuits that drove those gas wells. Well, when they did their rolling blackouts, they turned off the gas wells. So they turned off the gas supply coming to the power station. And so the generator failed. And so they didn't think through the design of the system and plan for problems. So again, going back to you've seen this diagram. I'm sorry, I'm running over here. but you can see, again, these only two connections to the outside world were DC, and they're small. And so nobody could save them. They couldn't import electricity to save the situation. So in 2009, in February 9, the ERCOT board, they discussed the cold storm for about 40 seconds. That was all. And they created an inadequate demand forecast, so they weren't ready. Then weather forecasters predict several days of freezing weather. The governor issues a disaster declaration on the 12th. And ERCOT starts sending one of those public warnings of, hey, hold back if you can, because we're going to have possible rolling blackouts. And then February 15th, they instituted the rolling blackouts. And temperatures got down to 12 degrees. By the 17th, 2 days later, there were 2.8 million Texans without electricity. They ended the outage 3 days later. So they had 3 days of blackouts, and the temperatures returned to 46 degrees. Sorry, I'm running over here. And so just a little view here of the timing. You can see this is on the left-hand side is the cycles per second. And this is time down here. And so you can see generation power outages and so forth. And so the cycles, it degrades and degrades and degrades. And for 4 minutes and 23 seconds, they were down to 59.4 hertz. If it had been had been low for 9 minutes, generators everywhere would have shut off. And so they were able to bring it back and start getting generation back, the load and the generation back in operation. But this was a scenario. If it had gone the wrong way, the lights would have been totally out. So how do you fix it? They got to implement those weatherization standards. They got to restructure the energy market to pay for reliability. They have to have more on-site fuel. They need to understand what the gas facilities that are powering these plants, which ones, and get them on critical circuits. They need to start paying attention with climate change. They need to start paying attention to housing efficiency. They need to define the rotating blackout process. They didn't have processes in place, and so they were all scrambling. They need to invest in batteries. They need to practice. They need to get better at communications, and they need to focus on cheaper electricity, but not cheap electricity. So again, I'm sorry I've run over, but in summary, it's been an incredible evolution over about 140 years. It's one of the largest machines man's ever created. It is fundamental to our society. Market is driving the elimination of coal. They're moving to large-scale renewables. That's going to require significant storage capability, better balancing tools, and a significant investment in transmission to get the energy created by the sun to move it in parts of the country that don't have that capability. And then we need to advance more zero carbon dispatchable technologies, hydrogen fuel cells, and small modular nuclear reactors. Nuclear reactors can be built very safely now, and we've got to figure out a way to get society to move on, because it's very important to our future. So sorry I ran so long, but if anybody's still out there, I'm happy to answer any questions.
You do have plenty of people still out here. If for those people who can stay, there are a lot of questions in the chat. Susan Couch, did you want to go ahead and field those questions?
Well, Susan, I see one question and I'll read that out. How is the energy balance between supply and demand?
So let's see, hold on a second. I'm sharing my screen. So let me go back a minute.
And while you're looking for that, I actually see that people were direct messaging me, which is also totally okay. But there's about 5 or 6 questions. So if you can stay and you're able to, we'll go ahead and hit those questions in a moment.
So let's go back to BPW, and so because it's something we can all sort of wrap our heads around. So again, the way that balancing occurs is the generation has to balance the demand, and so they have tools, they have computer systems and so forth that allow them to increase the speed of that generator, those jet engines we talked about. They increase the speed and generate more electricity, or they reduce the speed and generate less electricity. So they follow the demand, and they have computer systems and controls on these generators that allow them to balance that demand on an ongoing basis. The decision I talked about here is sort of that bigger decision of when you've cranked up the speed so fast it can't go any further. What do you do about that? And so it's a combination of people and computers that are making those decisions.
Okay, we have a second question here. Does industry account primarily for the great disparity in Eastern and Western interconnections? If not, why the disparity?
Population. I tried to get some numbers on the number of people and the density of the eastern portion of the grid, if you will, versus the western portion. But I couldn't get my hands on those numbers, but it's basically population.
Okay, here's another question, pretty interesting, and hopefully it doesn't disappear from my screen. Is the grid protected from electromagnetic pulse from an atmospheric nuclear bomb blast?
I can't answer that specifically. I would, you need somebody smarter than I am. I would say no, but I mean, circuit breakers would fire everywhere. But I honestly don't know the answer to that question. Anything I say I'd be guessing. So I'm not the right person to ask. I apologize. I'll try and find the answer though.
Okay, the next question. What do you think of the iron air utility scale batteries being produced by startups?
They hold a lot of promise. What this individual is talking about is, there was some recent articles about it in the Wall Street Journal. One of the startups is working on a battery system that is basically vats of balls of iron, and they're basically rusting them, and that through chemical reaction causing them to rust and then causing them to recede. And through that chemical reaction, they're discovering that it's a very effective way to store electricity. And so the scale of those, if they can scale up, and they're working on it, what you need is a battery that, what they're talking about is a battery that can potentially discharge over about 6 days. And so it holds a lot of promise. There's some other technologies. I haven't studied this in great detail, but there's a number of large scale battery technologies. The pictures that I showed you are more based on, and I've forgotten all the different chemical, but the types of batteries that are in cars, I apologize, I know more about this, but I can't pull it to the front of my mind. They're much more expensive and not effective for long term. And so the iron battery, that holds great promise, but there's others as well.
Next question. We have several questions coming in. This is great. There has been a lot of residential rooftop solar installed lately. Do you know what % of the total energy in our area is produced by home solar?
I don't know the answer to that, and that getting that information is not easy. I did spend a bunch of time studying how they do it, because basically what you're doing is you're sharing energy based on the physics of how the grid works. What you're doing is you're sharing energy with your neighbors, because electricity between the source and the destination. The physics say it's going to take the least path possible. And so if you have solar panels on your house and you're generating more than you need, your meter's running backwards. And by the way, there's a debate there. It's been in the state about you buy electricity at the retail price. And originally the MPSC allowed you to sell the electricity back to the utility at retail rates. Well, that isn't, and so the utilities argued against that. And I don't know what the current status is, but they were arguing, hey, you're generating electricity like everybody else. And so you only should get paid the wholesale rate. I don't know where that finally landed, but in effect, you're helping your neighbors because it doesn't go much further than that. But specific numbers, I don't know.
Okay, the next question. Much concern about hacking into our energy grid by enemies. Please comment on vulnerability.
So great question. In fact, I'm doing a class in the fall on hackers and what it takes to defend against hackers, because I had to do it for the last 15 years of my career. I would tell you that, you heard about the Colonial Pipeline hack job and so forth. The electricity, FERC and NERC in particular, has established rules way earlier, a long time ago, of the rules, the security rules that the utilities have to follow to protect us. So I think the electric grid is very well protected. I can tell you in my case, my job, because the government, the thing that's happening that you hear so much about break-ins is so many companies don't take security seriously. Well, in my case, I worked for a company that we were, one of the things is I processed about 30 million credit cards a year. The credit card companies made us toe the line. And so I had a lot of staff and spent millions of dollars doing that protection. And so there was motivation on my part. A lot of these companies that you hear about don't have that motivation because nobody is forcing them to do it. And so in this case, NERC has major regulations out there as it relates to security of the systems. So I feel pretty comfortable about that. Doesn't mean they aren't trying. And when I had a CIO job, every second people were pounding on trying to get into our grid, or into our computer system. So it's a very real thing, but I think NERC's done a pretty good job.
Here's another question. What about Alaska and Hawaii? Any governmental involvement in Americans' territories?
I didn't look into that one in great detail. I'm guessing that NERC applies, and probably FERC has less jurisdiction there, but I don't know. I had enough putting all this stuff together. I didn't focus on those two. I apologize.
Okay, here's another question. Does industry account primarily for the great disparity in Eastern and Western?
Industry is a factor, but I still say the biggest piece is population.
Okay. And here's another one that's kind of similar to what you answered already. How vulnerable do you think we are to foreign sabotage taking out the grid, which would paralyze government, banks, et cetera, and take more than weeks to rebuild?
I'm not overly worried. Again, the standards have been established and have been audited, and that's having experienced this. Auditing or establishing robust standards and robust auditing is very important, and I believe NERC's done a good job. I can't say that I'm an expert on it, but in my research for this, I did look into their standards, and they're very familiar. So I'm not saying, I would never say I was perfect. I never stood up when I had the job, when I stood up in front of the board of directors and said, I never said, I said, I've done everything I can, but I can't guarantee you that they're not in there right now. But I think NERC's done a good job.
Here's the next question. Is consumers building new capacity to replace the large amount that is being retired by closing the coal-fired plants?
We looked at that chart and they're buying a lot. Let's see, let me see if I can bring that one back up. Is it this one? Yes. So you can see here's the two that they're retiring here, in the orange. And if you look in the green, this is what they're buying to make up for the difference. The difference is they're retiring about 3,000 megawatts. They're planning on buying about 2,000 megawatts and so forth. So there's a difference, Beyond that, I don't know the details of their other plans. This is just what I was able to figure out publicly.
Okay, and here's another one. Although an efficient and clean source of energy, there is the trade-off of storage disposal of the used rods. Thoughts on this? Any talk of means to neutralize the waste?
So the answer to that one is the new nuclear power plant designs use a fraction of the fuel rods that the old designs required. So there's much less waste. I mean, I can't tell you the exact number, but it's a tenth or less of the amount of fuel in the old design, in the new designs versus the old designs. So they're just cleaner and more efficient in the new designs.
Okay, and I think this is the last question. Do you think the MPSC will approve consumers' energy shuttering Campbell and Carn by 2030 and feel confident there will be enough other sources to cover load?
So do I feel they'll be confident? Yes. So I'm going to explain this and give you a little bit more detail. So there, the catch is, and I didn't go into all this because it's complex. I mean, this could be another talk and somebody else probably have to give it, but the utilities, MPSC and others, there's certain regulations that have been established about the cost of these generation facilities and how much of that initial investment can be recouped at what rate. In other words, limiting how much they can charge for energy based on depreciating that asset. So, and hopefully this makes sense. And so the consumers was planning on running, let's say J.H. Campbell as an example, till 2035. And so they've moved it up 10 years. Well, that's 10 years of rate to recoup their depreciation costs that won't occur. So part of what you don't hear in the publicity is they're going to want some sort of rate relief to retire that power plant early and still recoup their original investment cost, which isn't unreasonable, but it will change our rates. And so that's the challenge. There's also a challenge, and this gets a little bit more esoteric. There's a non-regulated side to consumers and a regulated side. So what they're talking about is buying some of the utilities, some of the generation facilities they have in their non-regulated side and putting it into their regulated side. And again, that will have effect on rates. So it's all about the rates. So they made a proposal. And so what will MPSC, I mean, eliminating the pollution is a huge motivator, but is that enough to overcome the change in rates that will be required? And by the way, I don't know what that change is, but it will be a change. And so I believe they'll have the energy, but the dynamics and the pricing is yet to be determined, and whether that commission will approve it or not.
Okay, mine defaulted here back to the Hope College screen, so I don't see your screen anymore, David.
All right, let me stop my screen sharing.
Okay, and we're really quite over. We can certainly open it up. I'm actually doing work in the background, so I'm in no hurry. But you have 35 people still on the call. I have a couple just praises of your work. You've done a marvelous job organizing vast amounts of information, including science, history, and politics, making it understandable. Kudos. Just over and over again, you're being praised for a wonderful presentation. I would echo that. Just such a great presenter. Does anybody want to unmute themselves and ask a question before we wrap up? Is there anything that you'd like to discuss?
I have one question. I'm curious that recently, and I know in the past, I've been solicited to change my source of electricity or to some other entity, supposedly at a cheaper rate. Can you explain what that would be about? Why would I be approached as an individual homeowner?
Yes. So Michigan has like I say, all the state regulations vary. And so there's something called choice in Michigan. And depending on where you are and so forth, you can, if you look at your electric bill today, you get charged. If you look at the details, you get charged. I call it. You get charged for the electrons, and you get charged for the wires. And so you can buy your wire. I mean, the wires can't be changed, right? So the wires come to your house, and that's not going to change. But you could buy your electrons from somebody else. And so if the territory you're in gives you choice, you could buy electrons from somebody else. And so your bill would change, and the electrons, the charge for the electrons would now come from somebody else. You'd still have to pay for the wires, like if you have BPW wires, if you have consumer wires or whatever, you'd still be charged for the wires. And so that's a deregulation that exists. And so you might be getting offers like that. I don't know, for example, when in my conversations with Dave, I didn't find out if they support choice and so forth. It's not universal throughout the state. It varies. And again, it's a whole discussion in itself, but that's the theory of what you're being offered. And is that a good decision? I don't know.
I've typed a question twice, but I can't find it. So you can't find it.
So
Is that Peg?
No, Myra. When
Okay.
can I watch the class again? I need to redo it to have it sink in.
Sorry, it's not a simple topic. I apologize, but anyhow, I tried to do it in an hour and a half.
Well, if it's recorded, when can I rewatch it?
We will be posting all the recorded classes for summer towards the end of the semester. So I would look for it. We'll send out an announcement and a link mid to late August. So we'll make
Okay.
sure that you get that link so
Thank
that you
you.
can rewatch it. You're welcome.
I have a
I'm gonna go-
question.